Conditional probability. This is actually something that we've already talked about. We didn't do it with formulas, but we did talk about conditional probability when we were doing the two-way table stuff. Remember we were looking at the two-way table and I was like, hey, given that you were only looking at the children, which ones liked the roller coaster? You guys remember those kinds of questions? Okay, that is conditional probability because something was given to you. That's what makes it conditional. It's, well, given information. The moment information is given to you, it becomes your world, your denominator. It's the only places that you look. Well, we can do that with formulas and symbols and stuff, and that's what's down there in those boxes. So conditional probability. Given two events, event A and event B, the conditional probability of A given B is the probability that A occurs given that B already occurred. Kind of like what we talked about yesterday. Dependent events. What is the probability, if you guys remember back to yesterday's bag with the red, blue, and yellow? Like, what's the probability that I pulled a yellow marble out of this bag given that I already pulled that yellow marble out of the bag? The answer was 0, remember, because there was only one in the bag? That's conditional. It's conditional upon what has already occurred. Well, conditional probability is written as that A vertical line B. And that vertical line in probability is read given. So A vertical line B is A given B. In a class of 25 students, 14 like pizza, 16 like iced coffee, 1 student likes neither, 6 students like both, 1 student is randomly selected from the class. What is the probability that the student does some things? Guess how I started the question. Guess how I started the question. A Venn diagram. I used a Venn diagram because Venn diagrams make things very, very easy to organize visually.
That is so obvious. I'm surprised you didn't know this was me. Who else does their homework in pen?
Here's event A. Oh, you know what? It's not event A. What is it? It's iced coffee and pizza. So we'll say this is pizza, and we'll say this is iced coffee. And let's fill out what we know. We know there's 25 of them. We know 14 like pizza, 16 like coffee. Okay, that adds to 30. 1 likes neither. All right, we got somebody out here. 6 like both. And since we know that 6 like both, we can fill in the crescent for pizza only. We can fill in the crescent for iced coffee only. The crescent for pizza only, there was supposed to be 14 students in there. 14 total in the pizza. 6 happened in both. So this number must be 8. So it still adds up to 14. And there was supposed to be 16 in the iced coffee circle. 6 are already accounted for. That means we have 10 left over. And then just double checking, yes, those 4 numbers do add up to 25. Cool. A. What is the probability that a randomly selected student likes pizza? Okay. This is probability of pizza. Well, that one's easy. That's 14 out of 25. Right? It's 14 out of 25. Don't overthink it. That one's simple. But part B, what is the probability that they like pizza given that they like iced coffee? So it's probability of pizza given iced coffee. So now the given information is your universe. You can only, and you could think of that given symbol as being a fraction bar. The stuff that's given to you afterwards is the denominator. Well, how many people like iced coffee? 16. Now, of those 16, how many of them like pizza? 6. Which you could reduce to 3/8, but you don't have to. So the probability that you randomly select a student that likes pizza from the entire pool of kids is 14 out of 25. But now I go, hey, I pulled a person. what's the probability they like pizza knowing that they like iced coffee? And you go, okay, well, there are 16 people that like iced coffee, and 6 of them like pizza, so I have a 6 out of 16 chance if I know that that person was a coffee drinker. Yes, Gavin?
If it's a given that he or she like say that it was flipped.
Say it was flipped.
Would it be 14 over?
If it was flipped, it would be 6 over 14.
Oh yeah, okay.
Okay?
That makes sense.
Yeah. It's not that bad with Venn diagrams, is it? Okay. So let's talk about the formula. Let's talk about the formula for conditional probabilities. Psst. If A and B are events, then the probability of A given B is equal to the probability of A intersect B divided by the probability of B. See, that probability of B is on the bottom. It was the given information. You see that? So the top is the and statement being divided by the only statement. Look up at the Venn diagram. Let's look up at this Venn diagram and use the formula. The probability of A intersect B. Well, where does A intersect B? Well, for us, that's where pizza intersects coffee. Oh, it's 6. Divided by the probability of iced coffee. Oh, there's 16 in iced coffee. See, the formula is obvious that it works if you just use a Venn diagram. Just doing some basic algebra. Oh, by the way, what's happening here? Just doing some basic algebra and manipulating the formula. So the book only gives us the one formula, the probability of A given B. But of course, this also could have said the probability of B given A, and it would still be the probability of A intersect B, but now we divide it by the probability of A. What this does for us is it gives us another formula for the intersection. Right now, the only formula we have for the intersection before today's notes is if I say the probability of A and B, you did the probability of A times the probability of B, right? Okay. Well, this is another formula for the probability of A intersect B. Or, yeah, the probability of A intersect B, if you multiply both sides of that fraction by or multiply that equation by both sides, stop, strike, reverse. Let's try this all over again. If you multiply both sides of the equation by the bottom of the fraction, there we go, you won't have a fraction anymore. Instead, you'll get 2 different equations for the probability of A intersect B. And that's what's in the box over there. So the probability of A intersect B is the probability of A given B times the probability of B, or the probability of B given A times the probability of A. And these are in your reference sheet in some form or another. Not all 3 of these, but they're there in some form or another. In a town, 25% of the residents own a cat, 55% own a dog, 30% do not own either. Draw a Venn diagram. Start there. Part A is draw a Venn diagram. So we have dogs and cats. All right, dogs and cats. And I don't use percents, I'll use decimals. Dogs, cats. In a town, 25% of the residents own a cat. Gotcha. 55% own a dog. Gotcha. 30% don't own either. Oh, okay. So I've got a 0.3 out here. So what does that tell me about the circles? What should the circles add up to? No, just the circles. They should add up to 0.7, 70%. Okay, but if I take the 25% and I add the 55%, that gives me 80%. So I am 10% over. That means 10% has been double counted. So the overlap is 0.1. And now we can fill in the crescents, because dogs is supposed to be 55%. 10 of it's in the middle. So the other 45% is over here. And cats is supposed to add up to... This doesn't work that way. The circle for dog has to add up to 55. And now it does, 45 and 10. And the circle for cat has to add up to 25, 10's in the middle, so 15%, 0.15 is over here. There's our Venn diagram. Just double checking, yes, that does add up to 1, okay. There's our Venn diagram that describes this town. BI. Find the probability that a randomly selected resident owns a cat, given that they own a dog. Probability of cat given dog. Using the formula. I'm going to use the formula. It would be probability of cat and dog divided by probability of dog. So that's the overlap, 0.1, divided by the entire dog circle, 0.55. And I'm not even going to pretend to know what that number is, so we'll grab a calculator. .1 divided by 0.55 is 0.18 repeating. So to 3 sig figs, this would be about 0.182. It's 181818181818. Okay. Cool. B2. Find the probability that a randomly selected resident does not own a dog. Probability of dog not, given that they own a cat. So probability of not dog, given that they own a cat. Now it would be very easy to just look over there and see the answer. But I want to show that the formula works. So I have probability of not dog intersecting with C divided by C, probability of C. So let's look to our Venn diagram and let's find all the places where everything that's not dog intersects with everything that is cat. Okay. Well, not dog is up dog. So not dog is here. So there's not dog. And here is cat. So we are looking for the intersection where they overlap. Where do they overlap? What number? 0.15 is where they overlap. So they overlapped at 0.15. And what is the probability of cat? Well, that was given to us, 0.25. So 0.6. 0.6. Not bad, right?
Lovely. I just like it when you got it. Makes it a lot easier.
Now, before I move on to the last example, I do want to ask you a question. And I'm going to do this off to the side of the notes.
You can be like, so what's the logarithm?
Probability of A intersect B. Isn't this formula the probability of A times the probability of B? That's the formula for an AND statement, right? But didn't we just find out that, sorry, I'm scratching myself, the probability of A given B is the probability of A intersect B divided by the probability of B. This is what I just showed you, correct? So why is this not true? Wait, shh, don't ruin it for everybody. Why doesn't that work? Now, intelligent comment. Because they're not independent. You see, this right here is only for independent events. But when you're talking about conditional probability, the only time that this is a true statement, the only time that this is true, is when they're independent. For example, what is the probability I roll a 2 given that I flipped a heads? 1 out of 6. Why? Because they were independent events. So the given probability crap meant nothing. That's why. But, please, but when they are dependent events, this is absolutely not true when they are dependent. I just explained why, Gavin.
Well, I know, but like, why doesn't the formula work? Like, where does it
Be-
come from?
Because if they're dependent events, then the probability of one happening affected the probability of the other happening.
So the number changes.
If they are independent, okay, so let's just do it like this. You ready for this? Gavin, you ready? Probability of heads given that I rolled a 6. This would be the probability of a heads and a 6 divided by the probability of a 6. Correct, Gavin?
Yeah.
Okay. Does the coin, common sense, does the coin care what I rolled on the die?
No.
Great. So that tells me that the probability of heads and a 6 is the probability of a heads times the probability of a 6, correct?
Yeah.
Well, there you go. So the probability of flipping a heads, given that you rolled a 6, is strictly the probability of a heads, which is 1/2, and that's because they are independent events.
Yeah.
Now, let's say that I have a spinner. Just trying to make this up on the fly, so hopefully this works out well. And let's just shade 3 sections in, okay? Now I got a spinner, and we're gonna spin this bad boy. So there's a spinner, that was artistic. And then, oh, you know what? How about yesterday's box of petunias? The boxes of petunias, how about that? Where you had 6 flowers in each box. Like this. And we have like purple in 4 of them and purple in only 1, like that. So I could say, if you spin a shaded one, then you pull from box A. If you spin an unshaded, then you pull from box B. So if I ask you, what is the probability that you pull a purple flower? Doesn't it depend upon what the spinner said?
Yeah.
Well, there you go. So therefore, if I said the probability of a purple is actually going to be made up of 2 different scenarios. There's, well, I spun shaded and tried to pull a purple, or plus, I spun unshaded and tried to pull a purple. See how I'm using these or and statements here?
Yeah.
So the only time this stuff in red is true, the only time it literally cancels out, is if you have independent situations. And if the conditional probability formula is not equal to the probability of just one of them, you have proven that they are a dependent situation.
Okay.
See, that's how you can prove something is independent or not, is by attempting to use conditional probability. Back to our notes. Yeah, that was the correct number of button presses. Okay, the infamous can of soup question. I've seen many IB brains pop on this question. Okay, and I'm going to do my best to explain it. I'm going to use a tree diagram. We will not use common sense, because common sense fails a lot of highly intelligent people. We will use a tree diagram. The top shelf in a cupboard, you're going to want to pay attention. Somebody smack her. Not me, I'd get fired. Anyway, the top shelf in a cupboard contains 3 cans of pumpkin soup. That's the appropriate time of the year. And 2 cans of chicken soup. The bottom shelf contains 4 cans of pumpkin soup and 1 can of chicken soup. Lucas is twice as likely to take a can from the bottom shelf as he is from the top shelf. Suppose Lucas takes 1 can of soup without looking at the label. Let's determine the probability that it was chicken. Okay. That one's not too bad. That one's not too bad, I'll be honest with you. Because it's pretty simple. It's probability of top shelf and chicken, or bottom shelf and chicken. The and statements, multiplications. The or statement, add the 2 products. Very simple.
But don't you have to multiply it by like 3?
No. But the next one, determine the probability that can of chicken soup, determine the probability that can of soup was taken from the top shelf, given that it was chicken. Whoa. Okay. I'm going to draw a tree diagram because I think that makes life easy. So I have top shelf and I have bottom shelf, right? So shelves are wood. So I have top shelf. You know what? I'm going to write this smaller. And you know what? I'm not even going to write words. I'm going to say top and bottom. Top shelf, bottom shelf. So I could have taken the top shelf, or I could have taken from the bottom shelf. Now remember, Lucas just closes his eyes, spins around in a circle, reaches in, and pulls out a can of soup, okay? So he doesn't know what shelf it came from. He doesn't know what kind of can of soup it is. He knows he's just got soup because Lucas likes to be surprised. Now, on the top shelf, you have 2 options. You have pumpkin soup and you have chicken soup. And you know what? You have the same 2 options down below. So we have pumpkin soup and chicken soup, and today our soups are green. Why not? We have pumpkin soup and we have chicken soup. We have pumpkin soup and we have chicken soup. They both went bad. That's why they're green. Okay. Let's fill out the probabilities of the soups first, because that's easy. Easy. Top shelf. How many cans of soup are there? 5. 3 of them are pumpkin. And 2 of them are chicken. Now we go to the bottom shelf. Also 5 cans of soup, but this time 4 pumpkins. Easy peasy, right?
Yeah.
But now let's talk about the probability of the shelves. Lucas is twice as likely to pick the bottom shelf. No, sorry. Yeah, twice as likely to pick from the bottom shelf as he is the top shelf. So what's the probabilities?
It'd be like
1/3 and 2/3.
Yeah, that's what Mark was going to say. 1/3 and 2/3. Yeah, Ethan's remote now.
Wait,
What?
why would it be 1/3 and 2/3?
Well, let's talk about it. Listen. Let's talk about it, Gavin. If we said the probability of the top shelf was 1, let's just forget for a minute that 1 means 100% true, okay?
Yeah.
Then the bottom would be 2. Well, if you add those up, you get 3, right?
Yeah.
Okay, but the 2 branches always have to add up to 1, don't they?
Yeah.
So then you would divide by 3. So you'd have 1/3. and 2/3. So they add up to 1.
Is that gonna be like? Is that gonna be true? Like, say if it was 3 times as likely, you're gonna have 1 and then 3, so the bottom would be 4.
Yes. So if one was 4 times as likely as the other, you'd have a 1/5 and a 4/5. Yep. You just add them up, and that is the denominator. Yep. So these probabilities, we say bottom shelf is twice as likely. So bottom shelf is 2/3, top shelf is 1/3. Cool. Let's do part A. Part A. Probability of chicken. I'm going to use a highlighter, but I will be erasing my highlighters as I go. Okay? Just so I can. Actually, I don't know if I'll be able to erase my highlighters very easily. Let me do something real quick. Let me lock that. And let me trying to figure out how to make this. I want to be able to draw on this thing. I'm not going to be able to. Never mind. It's just not going to be able to happen. It's okay. Okay, probability of chicken. So your job is to look at all the branches that end in chicken. I see 2 branches that end in chicken. That means it could have happened one way or the other. And anytime you're forced to say or, you add. Now, it's impossible that you pulled that chicken from 2 different shelves. That's impossible. So there is no overlap. We don't have to worry about the subtracting the overlap. Impossible. They are disjoint. The 2 shelves literally have nothing. There is no zone that is both top shelf and bottom shelf. Okay. So all we have to do is add the 2 probabilities of chicken together. So that is going to give me the top branch of chicken is 1/3 times 2/5. Or the bottom shelf chicken, 2/3 times 1/5. And that gives me 2 out of 15 plus 2 out of 15. Okay, there's a 4 out of 15 chance that randomly pulling a can in that can of soup would be chicken. Not scary yet, correct? Okay.
Right.
Part B. What is the probability this can was taken from the top shelf, given that it was chicken? So here's how I want to do this. This is probability of top given chicken. Fine. The formula tells me that is probability of top and chicken divided by the probability of chicken. Hey.
Wait.
Yes? Okay?
Yeah.
Okay.
Sorry, I didn't know, like, the formula, like, the formula you wrote underneath the one,
Yeah.
the actual one, is it just showing how I can be, like, interchangeable?
Yes, it was just showing you that you can reverse it.
Okay.
Yes, the conditional probability formula I wrote in the same formula, it's just written in the other order.
Okay.
Okay, so question, guys. Are the shelf and the soup type independent? No, they are not. Because if I said to you, hey, what's the probability you pulled a chicken soup? You could just say 4/15. Or you could say, that depends on what shelf it came from. So this is not an independent situation. If it was an independent situation, I would literally just do the probability of T, 1/3, times the probability of chicken, 2/5. And I could just, or can I do it that way? Oh, never mind. Yeah, no, I could do it that way. I'll be all right. I'm thinking of the old way I used to do it without the tree diagram. This question is a nightmare without the tree diagram. Okay. Yeah. So these things are not independent. And the way we know they're not independent is because in a moment, we're going to see that the probability of chicken doesn't just cancel out and tell me that the probability is 1/3. If my answer to this was 1/3, then I would know they're independent events because the probability of C would have canceled off the top and bottom, right? But because it's not going to be equal to 1/3, you're going to see, oh, they must have been dependent. So how do we do it? We do the probability of, no, actually, we're going to travel down the path and do the multiplication. The probability of T, 1/3, and chicken, 2/5. Divided by probability of chicken. Hey, we just found the probability of chicken, didn't we? I wonder why they would have made me do that. That seems rather IB-ish, doesn't it? Bless you. Cool. Let's make some more space. Let's color the board white. There we go. And by the way, you could do this without a calculator. That's going to give me 2/15 divided by 4/15. Do you guys remember how to divide fractions? Yeah, so you're actually multiplying by the reciprocal. So this is 2/15 times 15/4, which can cross cancel. Gets you 2/4, which is 1/2. Not 1/3. You see, the probability that you pull from the top shelf is 1/3. But we just found that the probability of pulling from the top shelf, given that I'm holding a can of chicken, does not equal 1/3, which means these are not independent events. They must be dependent because P of C didn't simply cancel off the top and bottom. Neat. Question?
Okay, so it's like the probability of grabbing like pumpkin versus chicken was the same on both the top and the bottom. They would be independent.
Yes. So Parker said, what if the probability of pumpkin and chicken were identical on the top and bottom shelf? Like the top shelf is 3/5, 2/5. If the bottom shelf was also 3/5, 2/5, now they're independent situations. And it wouldn't have mattered. And the answer would have been 1/3. But because they were not equal probabilities on the shelves, it forced a dependent situation. So cool.